Alright, today we are doing section 4.3. We are going to prove triangles congruent by side, 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 or SSS. Our objective is to use side lengths to prove that triangles are congruent. First, we are asked to write a congruence statement for those triangles that are given. John, did you come up with one?
Angle,
Not just angle, the whole triangle.
PRQ is congruent to ONN.
Triangle PRQ is congruent to triangle. What did you say?
MNO.
MNO. And out of that, I could get on board with. Okay. So we have to be careful when we say a congruent statement to make sure that congruent parts are getting matched up. So the first one you can usually list out any way you want to, unless it's already given for you. So we could choose for the first triangle which letter to start at and work our way around. So we did PRQ. So that means when we start our second part of our congruent statement, we have to start with the angle that's congruent to angle P. That would be M. They both have one arc in them. Then the angle congruent to R, that would be N. And last, the angle congruent to Q, which is O. Have to go in a specific order for our second one. Questions about it? Okay. 2, how do you know that angle N is congruent to angle R? Ari? N and R are blank. That angle and that angle don't have anything in them.
I know.
Taylor? The third angle's congruence theorem is all we had to say for that one. She had her hand up first. I'm sorry. So, the third angle congruence theorem tells us that if we know that two angles in one triangle are congruent to two angles in another triangle, that the third angles from each are congruent to each other. We talked about that yesterday. Questions, concerns, need more time on our objective or warm-ups? No? Okay. Then we will continue on. We have a postulate. Remember that postulates are accepted without proof. So this is the SSS or side, side, side postulate. If 3 sides of one triangle are congruent to 3 sides of a second triangle, then the 2 triangles are congruent. Yesterday, how many congruent statements did we have to make to be able to say 2 triangles were congruent? Altogether, what did we have? How many statements? 6 statements. We had to say all the sides were congruent and all the angles were congruent. Today, this is like a shortcut. It's saying all we have to know are that all the corresponding sides are congruent. We don't have to know anything about the angles, and we could still say 2 triangles are congruent to each other. You see how this is different from yesterday? We're shortening things up a little bit. All right, we are supposed to decide whether the congruent statement is true and explain our reasoning. So we have to decide, do we believe that triangle JKL is congruent to triangle MKL? Well, if that's going to be true, then side JK better be congruent to which side? MK. Is that true?
Yeah.
Yes, because they're both marked with 8. So we know those are congruent. That's fine. Side KL better be congruent to which side? KL. How do we know that KL is congruent to KL? Okay, they share the same side. If this weren't a proof, why would I say something's congruent to itself? Some people are saying it. The reflexive property tells me that any segment is congruent to itself. So we can mark that one as congruent to itself. Lastly, side JL better be congruent to which side? ML. Is that true?
Yeah.
Yes, because they both measure 9. So we could mark those as being congruent as well. So, yes, all pairs of corresponding sides were congruent. So we should agree with this. All pairs of corresponding sides are congruent. That is enough for our explanation. Questions about example 1? All right, on example 2, let's go through the same process. If these two triangles are going to be congruent, then RS better be congruent to what? TV. Is RS congruent to TV?
No.
No, or at least we don't know, right? They didn't mark that for us. We don't know anything about RS or TV. So do you think we're going to be able to say that these triangles are congruent? No. So we could just say not enough information. We don't know all the sides. Something along those lines. Put big question marks by these sides. We don't know them. We cannot definitively say that those two sides are congruent. So we can't say that those triangles are congruent. Questions, concerns, or need more time? Okay, that's a lot of what this chapter is introducing us to different ways of telling whether or not triangles are going to be congruent, aside from knowing absolutely every side and every angle. All right, so we're just going to jump on into it and write a 2-column proof. This one should be pretty short and sweet because they gave us a good amount of information. So we set up our 2 columns, statements and reasons. What belongs in my first statement? My given information. So that would be that MA is congruent to side SO. And side or segment AS is congruent to side MO. I would recommend going ahead and marking your given information as you go. So MA congruent to SO, they each get 1 tick mark. AS congruent to MO. And my reason, of course, is given. Anybody have any ideas of where we need to go next? Ari, what do you think? Very good. If we are going to use this new postulate that we just learned, then we better talk about all the sides. So that means we need to say side MS is congruent to side MS. And I believe I already said it, but what was the reason for that? The reflexive property. The reflexive property is going to be one of your best friends when we do triangle proofs. So, do we have enough information to make our proof statement? Yes, because we've got all of our pairs of sides congruent from one triangle to another. So we can say triangle MAS is congruent to triangle SOM. Now, one thing that I do want to point out real quick is that if we look at that congruent statement that they gave us, here, angle M, they're saying is congruent to which angle? S, which is a little strange, right? But they don't necessarily mean this whole angle congruent, like we're talking about angle AMS probably. AMS would be congruent to OSM. OSM. When your triangles share vertices, it might not always match up letter to letter. Does that make sense? The M's will be in different positions. And we just kind of have to think about our angles using 3 letters rather than just 1 letter. Are we okay with that? Okay. All right. Anybody think they know my reason for saying this? Atea? Good. The side postulate. If you were to just put SSS, I would be okay with that. We will be learning more of these little 3-letter acronyms, abbreviations more like, for other ways we can show that they're congruent next week. Questions, concerns about our first proof for today? Ready to go on? Okay. This next one is a little bit longer than the last one, but it's still not bad. Once again, for my statements, I need to start with my given. Now, you, I believe, know by now that depending on if you're using something I made versus something the book made versus something somebody else made, some people like to split their givens up. I like to do it all at the beginning. If you have your own preference, that's fine. G is midpoint. All right. Either way, if you're listing out a given, your reason should be given. Now, let's deal with that first given statement. Fj is congruent to Hj. That's pretty easy. I can just mark it in my diagram. Next, I'm told that G is the midpoint of, should have finished that off, of FH. What does that mean to me? Majay?
That it's right in the middle of it, so FG and GH are the same.
Good. So I'm going to stick with congruence as opposed to equal, just so that I don't have to add other steps in there. But if G is directly in the middle of FH, then FG is congruent to GH. So I could make that statement and mark it, but I have to give a reason for it. Definition of a midpoint. Very good. Do we have enough to make our proof statement? No, we've only got 2 pairs of sides. We need that third pair. What is it? Good. I don't care if you call it JG or GJ. Either way, it is congruent to itself by the reflexive property. Questions, concerns? See, proofs aren't so bad.
When you do it with this, isn't bad.
This isn't bad. I've just been asking and everyone's been telling me the answers. I haven't had to tell you the answers. Now do we have enough to make our proof statement? Yes. We sure do. It's always nice when they give us the congruent statement. FGJ is congruent to triangle HGJ. My reason would be side, side, side. You'll notice a trend. We learn a new postulate, we use it in our proofs. That'll be a trend you'll see for the rest of the chapter. And of course, if you would like, you could mark that third side congruent to itself in your diagram. I do want to point out that when we make congruent statements about triangles, you better be putting your little triangle in front of it. Telling me what you're talking about. Same thing when we did the bars to talk about sides, or we put the little angle to talk about angles. I want to know what you're talking about. The only ones that don't get a symbol of sorts would be polygons bigger than a triangle. For example, when we had that pentagon in the homework and I wrote it up here, I didn't put a little pentagon in front of it. If it's got more than 3 corners, 3 points, then you just list the letters and it's fine. Okay, but for triangles, I better see your little triangle. Questions, concerns? Ready for our last example? Okay, I'm going to warn you going into this that, in my opinion, this example takes a minute. There's just a lot we got to do with example 5. Okay, we are given vertices for 2 triangles. We are asked to graph them in the same coordinate plane and show that they are congruent. So let's just start with the graphing part of it. I am going to do this a little differently just so that I actually have a grid. So bear with me for a moment. I'm going to list my coordinates off to the side and then switch to graph paper or graph board. It's not really paper, I suppose. -2, 2. I don't know why this PowerPoint was created without an actual grid and just with axes, but not a fan. -1, -3. Okay. Let's switch to some grids. That's not great. It's a little better. All right, if I'm graphing the point -2, 4, where am I going? Left 2, up 4. 1, 2, 3, 4. Very good. What about B at 4, 4? Right 4, up 4. 1, 2, 3, 4. 1, 2, 3, 4. B. C is at -2, 2. Left 2.
Wait, are we supposed to
Up
randomly
2.
put it on?
Yes.
Yes, you'll have to draw on your own tick marks. I cheated because I have an iPad. Try to make your tick marks evenly spaced. Man, it doesn't have to be perfect. There's our first triangle ABC. Now let's graph LMN. -3, -3. Where do I go?
Left 3 down 3.
Left 3 down 3. What about -3, 3?
Left 3 up 3.
Okay, there's M. And N is at -1, -3.
Left 1
Left 1
down 3.
down 3. Okay. Kind of cut off point C there a little bit. All right. Now they asked us to decide if these triangles are congruent to each other. This isn't going to be as bad as I thought it was going to be. What makes this a little bit easier as far as figuring out side lengths? You can count the boxes on a few of them, right? So for example, side LN has a length of what? 2. 2 boxes, 2. What about LM? 6. AC is 2, and AB 6. So if these triangles are going to be congruent, I just need to find how many side lengths. Well, 2 more are left, right? Like 1 for each triangle. Does that make sense? We've only got 1 unknown side in each of these. In order to find those unknown side lengths, I need to use the distance formula. It's just never going away. So if I'm finding the distance from B to C, my first x coordinate that I'm using, 4 minus -2. Subtracting a negative means I'm really adding. My y coordinate that I'm starting with, 4 minus, also gets squared. What is 4 plus 2? Square it. And 4 minus 2, square it. Add them together. Square root of 40. If you want to simplify that, you can. But you don't really have to, because all we're really trying to figure out is mn going to be the same? Right? So, let's find our length of mn. Put that up at the top. First x coordinate, -3 minus, subtracting a negative means I'm really adding. First y coordinate, minus, so we're really adding, adding 3. -3 plus 1 is -2, square it. 3 plus 3, square it. Add them together. So are these sides congruent? Yes, they sure are, because they both had a measure of square root 40. It's hard to fit that all in there. It's getting a little cramped. So we have shown that these two triangles are congruent by finding all of their side lengths. Let's see, what did it ask us to do after we said write a congruent statement? So, which triangle do you want to start with? ABC, sure. So we would say triangle ABC is congruent to triangle LMN. So let's just make sure side AB should be congruent to LM. Check, they both are 6. BC, congruent to MN. Yep, those were the ones we just found. And then AC to LN. Those ones were both 2. So yes, we do have it in an okay order. You could mix the order up and it would still be correct. For example, you could say triangle CAB is congruent to triangle NLM, and it would still be fine. That's why answers can vary. It depends on where you start. Questions about the congruent statement? The last thing they ask us about these triangles is, are they right triangles? Anybody have any feelings about it? You think they are?
Sure.
Okay, why do we think they are? How do you know they're perpendicular?
We don't know. We have to find the slope.
Okay, so we need to show slope, which is actually super duper easy on these. What is the slope of any horizontal line? 0. So our slope for LN is 0. It's not great notation, but we're going to go with it. What about our slope for ML? Slope of any vertical line? Undefined. Which means that it would have to be some number like 1 over 0. So yes, any two horizontal and vertical lines are always going to be perpendicular. So yes, these are going to be right angles. Do I need to bother showing my slope again for triangle ABC? Why not? They're congruent. We already said they're congruent. So angle L and angle A ought to be both right. They should be congruent. If we looked at our slope for one of them and found that it was a right angle, then the other one should also be a right angle. Not so bad since they gave us some vertical and horizontal segments to work with. Would have been much more involved if we didn't have those, because then we would have been using the distance formula 6 times. That's always fun. Questions, concerns?
Yes.
Warm, fuzzy feelings about side, side, side? No? No warm fuzzies? Side, side, side should be easy. We don't have to worry about the angles at all. Okay.
Yes.
All that disappears. Our homework should be on your assignment guide, but here it is.